Thanks for the kind introduction. As Mark said, my name is Avneesh, and I'm a PhD candidate at Carnegie Mellon, working with Chris Dyer primarily. And we're working on some interesting problems at the intersection of machine learning and natural language processing. In particular, what I wanted to talk to you today about is how we can kind of take models in translation, make them contextually richer, but not necessarily do that with such an increase in model size and model bloat, so how we can handle it in a low-dimensional framework. And I just wanted to actually emphasize before I dive into the presentation that the models that we propose here really reason about context in a low-dimensional space, and MT, or machine translation, is simply an application of a lot of these models. And in fact, the ideas here could be applied to a lot of different areas. I'm just a fan of MT because I think it's a nice way to validate certain ideas that you have about natural language processing and validate them in the wild. I think you come up with some very unique scenarios, and it's very integrative. And on that front, before I dive in, I actually just wanted to talk a little bit about what MT guys are maybe doing over here and so forth. And so I actually think that there's a lot of similarities between the kinds of problems that you guys work on, or my understanding of what you guys work on, and the kinds of problems we work on in MT. They are similar in maybe how we should incorporate context. So for example, one thing that I know you guys use a lot is monolingual word or phrasal alignment, and the same kinds of considerations or similar kinds of considerations that we use in MT or that we look at in MT could be used also in the monolingual case. And in particular, I also think that there's a recent line of work on, for example, mapping natural language sentences to logical forms. Luke Zettelmoyer and his students, or when he was at MIT, they did a bunch of work on this stuff where they were looking at mapping, combinatorial categorical grammars to logical forms. And this is actually, in my opinion, a translation problem. It is a tree-to-string translation problem, and actually, in the sense that you're mapping the CCG grammar into some logical form text. You can build a language model over logical forms and the like. So you can really look at this as if it were translation. And then on top of that, on top of these commonalities, there's also, I also feel that translation corpora or parallel corpora are an excellent source of semantic supervision. We've had things like paraphrase database, which is literally monolingual, basically phrases where you kind of pivot between a language you're interested in and other languages to kind of get semantic correspondences using word alignments. Also there's been some interesting line of work on multilingual embeddings, and people have realized that if we embed our words or into these vector spaces, but we take into account cross-lingual kinds of information, word alignments and the like, we can actually do better. And as I was saying, semantics is increasingly becoming very cross-lingual. And so I think it's important for MT and semantics to kind of work together on this front. And throughout this talk, I'm also going to touch upon a few applications that I think may be relevant to you guys here at AI2. So all right, well, without further ado, I'd like to kind of dive in a little bit and motivate why we need, for example, low-dimensional context-dependent models. Well, firstly, why we need context-dependent models in translation, and secondly, why we would like to actually make them or reason about them in a lower dimensional space. So say we want to translate the following sentence from German to English, and are there any German speakers here? Could you help me? I mean, I know what it means, but could you help me translate it?
These questions will cause him to ask more for cats.
About cats, right? Yeah, and so everyone loves cats, I guess, and the problem over here in this particular sentence is we have the German word fragen. And fragen can translate to either the verb to ask, as we see in the second case, or it can translate into the noun form questions. And so if we just relied on a lexical translation, a word-for-word translation model here, we might not do very well. And this is actually, so if we focused on these fragen, this is actually the main motivation for us to go from word-based models to phrase-based models in MT. So what exactly are we doing here? We're basically incorporating local context in the form of these surrounding words, but we're stuffing them into a larger translation rule. So what we're doing is we're not just considering words for translations, but considering phrases. So in this case, if I added diese, which is these, to fragen, I automatically, or I've kind of disambiguated it to a large extent to know that these cannot precede the verb form of questions. So this is very helpful. And like I said, this is one of the main motivations for going to phrases in machine translation and translating phrases as basic units. These rules or these phrases, the basic translation units we use, don't necessarily have to be contiguous. So we can have gaps, as I've seen here, so some hierarchical phrase-based phrases. And also, they can actually also contain some kinds of syntactic information as well. So just to kind of reiterate, basically, the basic idea from going to words to phrases is to make our models somewhat contextually richer. And there's been this implicit assumption that to make models contextually richer, we need longer translation rules. As I've mentioned before, instead of translating Fragen, we'll translate these are Fragen. We need longer translation rules, and we need larger translation models. And so what exactly happens here? So if we're going to do that, if we're going to disambiguate our translation options with these larger rules, we're going to come up with both computational and statistical issues. Computational, naturally, because of this, so in this particular case, we have this grammar constant g, which is the size of a grammar, the number of rules in my grammar, and that's naturally going to increase exponentially in terms of the length of the basic phrasal unit that I need to consider. We also have statistical issues as well, because for the very same corpus, now I have these phrases that are exponentially less likely to occur in the length of the phrase, and so the estimation is not going to be very solid. So I can throw in more data, but what's going to happen is I'm going to get more computational issues, I'm going to get more unique phrases that I haven't seen before, and so we have this whole model bloat issue. And so just to kind of make this a little bit more concrete, how exactly do we go from these word-based models to phrase-based models? Well, what we do is we can have this alignment matrix. So assuming a priori I've been given some word alignments which tell me which word aligns to which word or which word is a translation of which word, I can kind of extract these big blocks and chunks. So not only can I extract these individual word translations, I can extract the entire block. The same logic actually...
Sorry, can you explain what does red versus black mean?
Oh, so sorry. I just wanted red to just concentrate your attention on that segment. There's no distinction per se here. The red box simply means that I can extract these are Fragen werden and these questions will as an entire phrase.
Okay, and I'm still confused because I would expect Fragen and ask that cell to be colored somehow.
Fragen and ask is colored. Sorry, it's a little bit small, but Fragen and ask is also colored there. So what I'm just doing...
I see, the left is the sentence.
And the other one is the English sentence. Sorry, the left is the German sentence. So I'm just kind of giving examples as to how we get this massive model bloat here. So because...
Confused. I'm sorry to interrupt you because I thought you're showing the word level alignments in the cells.
I am. The word level alignments are in the cells. They are in the
word level alignments in the cells. Wouldn't the first Fragen also have an alignment with ask?
No. So that's basically I'm imagining this is the result of a priori some word alignments have been given to me. So I've already run a word aligner, and I found that in this sentence, Fragen in this particular case aligns to questions in this particular case. So essentially what I'm doing here is I'm extracting phrases from words. So I'm explaining how we can go from word level alignments to phrases in translation.
Right, and the input, which is what you're showing, is what you get from the word aligner.
But
I thought in your example you said that the word aligner would align Fragen with both ask.
No, it wouldn't align Fragen with ask. I'm saying in test time now when I see Fragen, so this is in training time. This is in training time when I'm going from alignments to phrases. In test time, I have no idea what the alignments are. In test time, I just see Fragen, and I need to figure out what it translates to.
So this is a distinction you didn't introduce before. You're showing a table that's the input at test time?
No. All I'm explaining now is how during training time, how we go from words to phrases.
Okay, but what does this table represent?
This table is during training time for a particular sentence pair, what the alignments are, and then based on the word alignments, I then extract phrasal alignments from the word alignments.
Right, and what I don't understand is the inconsistency between what you're showing in this table and what you said earlier. Specifically, you said that at training time, the word aligner would align Fragen with ask and with questions, right? That was the problem.
No. Sorry.
That was the problem that the phrasal alignment was solving. right? That was your example.
No, so that example that I gave is actually a test sentence. So if I wanted to translate that test sentence and I had a model, this is what, if I had a word-based model, it would be a little bit confused when it looked at Fragen. So that's what I'm saying. It's a word-based model. It would be a bit confused if it just saw Fragen, but if it had instead in the model, it had these are Fragen, then there's no ambiguity in terms of what Fragen means in that case.
So this is not the output of a word-based model. This is the gold input to your phrase.
This is now, yeah, so maybe basically the confusion arises because I use the same example for a test sentence, and now I'm showing that in training, how exactly can we take the word alignments and then extract phrases from it.
So I understand then these are two separate things. So my question then becomes, at training time, how does the model decide to align the second Fragen with ask but not the first?
Oh, that's actually, so during training time, the model actually works on the EM algorithm. So what it does is basically it looks at an aggregate over lots and lots of data and then computes partial counts basically. So it might be the case that initially you might have misaligned it, but then aggregating over partial counts and re-estimating their E and M steps, it should basically give you a distribution that this is, in this particular case, the Viterbi alignment. So the most likely alignment is that, Fragen aligns to questions in this training example. So I can get into some of those details later. It's not the main part of the talk, but I can get into some of those details later. What I actually wanted to show, though, is actually I wanted to emphasize this particular slide because it's somewhat important for the subsequent talk. And I think Mark was actually on this paper, actually. So over here, what the main idea is, we want to go from, like I said, these smaller word-based alignments or these minimal grammars, so to speak, to phrases. And I showed a couple of examples on the previous slides in terms of how we do word-level alignments to phrases. So what we do over here in the syntactic case, so if we have a syntax-based translation model, it's actually extremely similar. So what goes on in syntax-based translation is that we have a sentence pair. There are word alignments in that sentence pair. Like I said, I've gotten those a priori from a word aligner. And then the first thing I do is I can come up with the minimal explanation for that sentence pair consistent with the word alignments. So in this particular case, so say this is the particular word alignment in my training corpus, I can come up with these particular minimal rules from this word alignment. So a verb phrase and werden in VP lassen, and then another verb phrase here. And so what basically Gali and Mark and colleagues basically found out is that if I can then take these two rules, compose them, and then come up with this composed rule here on the right, and throw that into the grammar as well, I get a 3.6 blue point improvement. Obviously not just for this rule, but for rules on aggregate, I get a very large blue improvement, but I also get a grammar that is much, much larger, obviously, right? Because instead of just focusing on those two rules, I combine those two rules, and I throw that rule also in there, and I get a grammar that's much, much larger, but that performs much more effectively. So just to kind of make this distinction, so what I'm actually going to use, the terminology I'm going to use here is not necessarily words and phrases, but I'm actually, because some of the experiments or most of my experiments are in like a syntax or hierarchical based setup, I'm going to talk about the minimal versus composed distinction here. So what I mean by a minimal grammar is, like I said, I have rules in my grammar that I cannot decompose any further. So if I have rules in my grammar and I can't decompose them any further, and then that's a minimal grammar. If I have rules in my grammar and I can decompose them further, and those rules also exist in my grammar, then I would call that a composed grammar. So there's an example here. I have these two rules that can combine and can form that rule. And these are actual hard numbers that I ran on a German-English setup. So we have grammars that can actually be 40 times larger in this particular case. Naturally, the larger grammars, because there are more rules, are harder to index. They're harder to estimate because they're rules that I've seen extremely infrequently in the data. But at the same time, the minimal grammars are easier to index, but we know that they don't have as good performance. And so now the question is, can we really get the best of both worlds? And that's what I'm hoping to achieve over here. Another case study I actually wanted to show is when you're going from words to phrases, is actually looking at bigrams in your phrase table. So if I have a phrase table, and it's a phrase table, so it has bigrams, trigrams, and the like, and I look at basically an evaluation corpus. So I take an evaluation corpus. In this case, I take an Arabic test set, and I feed it into my phrase table. And I look at all the unknown bigrams in my Arabic test set. So bigrams that basically did not exist as phrases in my phrase table, and then I break them down into their individual unigrams. You actually find that in a vast majority of the cases, 85+% of the cases, both of the individual unigrams actually exist in your phrase table. It's just that they've never been seen together in combination. And so there's a lot of information, therefore, in the phrase table that we're missing out, and that we kind of are just discarding also when going when going from words to phrases. And this is actually a classic example of the statistical difficulties that we see here. So as soon as we go from unigrams to bigrams, we automatically get a lot of unseen bigrams, but a lot of the bigrams, if you decompose them further, are actually in our model. So a lot of this is actually a reliance on surface features, I would say, so relying on, for example, just the word identities and the like. And we'll talk about how we can actually address some of those issues. So another problem that actually also arises from very large grammars and is somewhat linked to derivational ambiguity, because if I have more rules in my translation model, and so when I look at it, just like in monolingual parsing, when I look at a sentence and I want to parse the sentence, I can come up with many different derivations or many different valid structures for that sentence. So in this particular case, when we want to do phrase-based translation, what we would ideally also like to do is first we segment our source sentence into various phrases. And then once we do the segmentation, then we can look at translations of various of the segmented phrases. So we don't do a hard segmentation. We might consider all segmentations that we can do, or all segmentations that match particular translation rules in our model. So this is one particular segmentation. I can do a word-based segmentation and then try and translate this word for word. I can segment it basically by looking at larger chunks. So this is another valid segmentation, and this is yet another valid segmentation. So there are generally an exponential number of segmentations in terms of the sentence length, and the problem with a lot of machine translation models is that all of these segmentations are considered equally likely. So they're a priori. There's no prior information for me to prefer one of these segmentations over the other. And what we'd like to do over here is incorporate context to be able to tell us which phrases we should prefer over the other before translating. So when segmenting, which ones we should prefer. So just to quickly recap, the motivation, we know context matters in translation, and moving from words to phrases makes sense in principle, because that way we can kind of incorporate more local forms of context, via our translation rules. Like think about Fragen versus diese Fragen. But then there are a lot of associated computational statistical concerns that we should address. As I mentioned, there's a very good reason to believe that the surface or syntactic features, in other words, word identities, or maybe even things like part-of-speech tags and the like, are inadequate in capturing the kinds of semantic distinctions we need in translation. And so we might need to actually do some form of parameter tying, I would like to call it, by doing working in lower dimensional spaces. And then the questions that I've specifically kind of outlined here are things that I'd like to address in this talk. Namely, can we actually use smaller grammars and handle the context elsewhere? In other words, can we basically use a smaller minimal grammar to tell us what translations are, and then use context and better parameter estimation techniques to basically refine those grammars in a particular way, in a context-dependent manner? The second question is, can we alleviate model brittleness? So out of vocabulary words, unseen word sequences, unseen phrase sequences, using context and using context in intelligent ways. And also lastly, as I mentioned, is there any way that we can a priori tell the model which particular phrasal segmentations it should prefer when translating from one language to another? And so the central hypothesis is that obviously context does matter, and its effect is low dimensional, and I'll actually talk about that on the next slide. And so what our goal is in this talk is we would directly like to leverage this low dimensional view to incorporate some very rich forms of context in translation models. On the low dimensional front, actually, this word is actually very popular these days, also known as, I guess, representation learning and the like. And before I wanted to go further, I'd like to just address this slightly. So a lot of people have been kind of looking at translation or modeling kind of semantic distinctions and the like using neural networks or deep learning. And the goal is actually very similar here. So the goal is to somehow increase statistical efficiency by operating and doing parameter estimation and just generally reasoning about your structures and reasoning about your information in a lower dimensional space. But then there are also some additional computational concerns on a lot of the neural network front. There's a lot, for example, first of all, we're not very clear as to what nonlinearities are adding or whether there's a very unique kind of low-dimensional representations that are being learned here. Naturally, a lot of the neural network approaches are very iterative, and I'll actually present some more one-shot estimation approaches based on singular value decomposition and the method of moments. They do require computations of partition functions, which I've generally tried to avoid here. But there are some very interesting potential connections between some of the recent work on neural networks as well as some of the stuff based on method of moments estimators and based on singular value decompositions and the like. And I think that's a very interesting area to explore. All right, so basically what I'd like to do is I'd like to take context and then I'd like to feed it into this box here. And what I'm actually going to do is I'm going to touch upon probably 3 of these works, the supervised, semi-supervised, and weakly supervised work. I know Ankur has come in and spoken to you guys already, and he spoke about the last portion, which is the unsupervised portion, the power low rank ensembles. So that's work that we did together, but I won't talk about that. What I'd like to actually talk about here is the important thing is that the latent spaces in all these scenarios, so the kinds of low rank spaces I'm working in, are actually all recovered in an unsupervised manner. And the amount of supervision I'm talking about here, semi-supervised, supervised, and the like, essentially dictates which basic units we're going to enrich with context. So, for example, in the supervised and semi-supervised cases, I need some kind of translational equivalence because I'd like to enrich the basic contents that I'd like to enrich are my translation units. So I'd like to enrich them more with context and so forth. So I need some seed information in the form of parallel sentence corpora. In the weakly supervised case, this is the phrasal segmentation case. I'll show you how basically we use some very weak form of supervision in the form of a paraphrase database to learn what we need to learn. And after that, we can apply all of our models basically without necessarily any supervision. So in the first case, as I said, I'll talk about a latent variable synchronous context-free grammar. And I'll talk about how exactly I applied it in the case of translation. In the second case, I'll talk about a graph-based semi-supervised method to enrich translation models with monolingual data. And in the third case, I'll talk about how we learned compositional functions and how we learned models that can score compositionality versus non-compositionality and how we use that information to then a priori tell us which phrasal segmentation should be preferred over others. Because the basic idea is if you have a phrase that translates, that is a non-compositional phrase, it should ideally translate as a unit. If you have a phrase that's fairly compositional, then it doesn't really matter whether you translate it as a unit or whether you can break it down into its individual words and translate. And like I said, the last part I'll not really address. So outside of all the theoretical contributions and so on, I just also wanted to briefly say why this all matters. We have smaller models with faster estimation. We can effectively use unlabeled data, as I'll show in the graph-based case. And also, for as far as I'm concerned, or as far as I understand, we've also done an initial effort at integrating some of this compositional semantics knowledge into MT. All right, so let's go back to this slide here. And this is actually the first slide that we saw this a bit earlier, and this is actually what I'd like to address. So we have these minimal versus composed grammars, and hopefully you understand the distinction. We have smaller grammars that don't perform as well but are faster and easier to index, and we have the opposite scenarios here. So the question is, how do we get the best of both worlds? Before I go any further, I just wanted to briefly kind of give a shout out to Hao Zhang and colleagues I use their minimal grammar extractor here. This is not that important in the grand scheme of things. There are other ways you can also extract minimal grammars, but the basic idea that we used here is we extracted these very small grammars using their paper and their code. And what we then tried to do is we tried to explore this transition between minimal and compose that I spoke about, but not by stuffing more information inside translation rules, so not by making translation rules necessarily larger and putting more words in them, but rather by trying to do that using these latent variable models. So once again, we have the following sentence. And so say we have a minimal grammar that describes the sentence. So this is a synchronous context-free grammar. You're generating strings in 2 different languages. So we have the German on the left, and we have the English on the right. And we have this particular word, fragen. So this is, say, in test time. And so we would like to figure out basically what exactly it translates to. And so the basic idea is we augment all of our non-terminals. And sorry, I should mention that this is a hiero or hierarchical grammar where you basically use the structure of the hierarchical structure of a context-free grammar, but you don't necessarily use the non-terminal categories. So you don't necessarily use verb or verb phrase or NN and the like. And there are particular reasons for that. One is data sparsity issues. The other is it's not necessarily the best idea to map monolingual parsing categories to translation. They might not map out too well and the like. So we have the following, only a single non-terminal in our grammar, that's X, but then we augment it with latent states. And the latent states, say, have 2 particular, like say the latent state size is 2, so they have 2 particular configurations. So the basic idea that we'd like to encode the context of a rule in these particular latent states, such that now when we come up to the test time, and we'll see basically that our latent state configurations are as follows, what we might do during test time is we might marginalize over our latent states using some form of the inside-outside algorithm, in other words, a generalization of the forward-backward algorithm for trees. So we'll marginalize over those latent states that I mentioned. And ideally, during marginalization, we should find that in the first case, fragen should translate, the translation of fragen to questions should be preferred over the translation of fragen to ask. And in the second case, when we marginalize over all latent states, and during marginalization, we're doing inside-outside, as I said, so we're looking at inside trees and outside trees, so we're taking into account the entire tree, we would ideally like to prefer the second rule. So what exactly we're going to do here, we have the synchronous CFGs. These are generalizations of monolingual CFGs. We're going to attach a latent variable model to them. And then these non-terminals are essentially going to be augmented with latent states, but we're going to do that in a context-dependent manner. So previous work may have taken, for example, a source-side parse of the sentence and then tried to intersect that, and then tried to basically provide more information to non-terminals using source-side parse trees. We're going to actually do that completely within the grammar in a context-dependent way. We're going to fix the minimal grammar, and then we're going to learn what these latent states are. And we actually learned these latent states using 2 methods, using EM and using actually something a little bit more interesting, in my opinion, the method of moments estimator, and I'll actually talk a little bit more about that. And the basic idea that I'd like to actually emphasize is that with a minimal grammar, so we saw that there was that whole performance gap between minimal and composed grammars. I'd like to emphasize that with a minimal grammar, along with this latent variable model, plus some intelligent dimensionality reduction, we actually managed to get performance that was equivalent, if not slightly better than, the equivalent hiero grammar. So what exactly are latent SCFGs? Just very quickly, what I wanted to do is, we have, for example, in a grammar, in our translation grammar, we might have rules of the form binary, unary, and preterminal rules. These are very similar to the monolingual parsing case, except we actually, like I said, are generating strings in 2 different languages. And the basic idea that I'd like to present is that for each rule, what we're going to do is we're going to attach these extra parameters. So we're going to attach a set of extra parameters. For a binary rule, the parameter is a tensor. So it's a 3-way matrix, you can think about it, because there are 3 non-terminals that we need to consider. The left non-terminal and the 2 on the right. For the unary, there's 1 on the left, 1 on the right. That's why it's a matrix. And for the preterminal case, it's just a single vector.
How is this generalized from what Matsuzaki did?
It's actually, it is fairly similar. I mean, Matsuzaki didn't, I think, talk about it in terms of vectors. And I didn't talk about it in terms of tensors per se. So I think they just had these latent states attached to the non-terminals. And actually, I know they did have these. They didn't just structure it in terms of tensors. They had H1s attached to. They had hidden variables attached or latent variables attached to non-terminals. So that's the idea of that comes from Matsuzaki. And then I think Slav Petrov also did something very similar as well. So this is a generalization in the sense that it's now in the synchronous case as opposed to the monolingual case.
Oh, Matsuzaki's was not for the synchronous?
Matsuzaki was only for monolingual parsing. Yeah. So the question now is, how do we learn these parameters that I've attached to these rules? And I just wanted to kind of give you an intuition now. So let's take a concrete example. We have the following translation rule. Werden ihn x1 lassen. We'll make him do something. And so we can look at this in different contexts in our training corpus. So werden ihn mehr nach Katzen fragen, as we saw lassen, or werden ihn weniger Käsespätzle essen lassen, etc. So we can see this in various contexts. And then what we can do is we can compute inside and outside features. So then this is for this particular rule, I'm going to look at features on the inside trees. And these features I'll give more information about later. There might be lexical indicators and so on. I'm going to look at outside features, so features of the outside tree. And I'm then going to compute the covariance of these features, so look at how they covary with each other. And then I'm going to compute a singular value decomposition of them. So then that's the basic projection that we're doing. We're basically kind of trying to project translation rules, like werden ihn x1 lassen, that have been expressed in terms of inside and outside features. We're trying to come up with lower dimensional representations of these rules using singular value decomposition. So the first step is we take these trees. So in this particular case, this is the particular non-terminal we would like to augment. We look at features on the inside of the tree. We can look at features of the outside of the tree. Features could be things like rule indicator features, could be lexical items and the like, and the same thing with the outside tree. We compute, like I said, the outer product or the covariance matrix between inside and outside features, and then we compute the singular value decomposition. So I'd like to emphasize here is that in the original space, phi and psi were our feature vectors, inside feature vectors and outside feature vectors. They were very high dimensional. They could be 100,000 dimensions and the like. What we've done now here is we've now come up with lower dimensional representations for these contexts, for the inside features and the outside features. And then what we're then going to do is in the lower dimensional space, we're going to compute the covariances now. So that's how we're going to construct each of these parameters. So as you can see here, I have a low dimensional representations of my inside and outside features, and I'm going to use those low dimensional representations to come up with these tensors that I can attach to various translation rules, these matrices and these vectors and the like. So then I'll just kind of quickly go over some experiments and then move on to the next section. So the experimental results are actually quite interesting. So the first thing I'd like to show is that these are the baselines, and that's the Hyro baseline over there, and that's the minimal grammar baseline over here. So we automatically see about like a 3.5, 4 point, sorry, yes?
That tensor you showed, was it just a product of 3 vectors?
Yes, it was just
a rank 1 tensor.
That's right, exactly. It was the product of, well, it's the product of 3 vectors that have been aggregated. It's a sum of rank 1 tensors. So you're summing over a bunch of these things. But these are the lower dimensional representations of my inside features and my outside features that I'm computing my tensors from.
Is this the Herapath-Can decomposition, or?
I think so. I think this is Parafac. I'm not sure, but like Parafac versus Tucker, right? I think this is Parafac. I'm not exactly sure though. But there are some relationships there, I believe, and I haven't explored that as much. Okay, so this is this gap that we saw and that's been well documented in the past. And then what we then do is we have our latent variable model and we start throwing additional ranks at it. And we see a really nice story here. We see that performance increases as we throw ranks. Interestingly, we try and throw in some additional features and some additional ranks, and performance goes down, which shows an interesting peak at m equals 16 for this particular data set. So 16 latent states. My tensors are 16 by 16 by 16 and the like. So that shows some interesting results. And we also compared it to the EM algorithm for learning these latent states, which also has a very similar trend, but is not as good as the method of moments estimator. And it's very interesting, actually, because the method of moments estimator is actually known to be statistically less efficient, but computationally far more efficient, because you don't have this iterative likelihood maximization thing that you're doing every iteration. You're just literally taking a singular value decomposition, coming up with lower dimensional representations and computing from there. So the basic intuition behind method of moments is you observe this covariance, you observe this covariance matrix in the data, this moment information. So second order moments you've observed in the data. You see how inside and outside features covary, and then what you would like to do is you'd like to do the reverse. You'd like to see what are the latent variables, what is the configuration of the latent variables that resulted in me observing this covariance matrix in the data. And so you're doing the reverse, and that's how you intuitively recover your latent variables. So so there's an extension of doing this without hierarchical trees, without trees. You can do this completely in a flat phrase-based setup, and I'm actually working on that now, but in the interest of time, I think I'll maybe skip over this. But the basic idea over here is that we can actually do the same kind of thing, but in a k-nearest neighbor space. So we can actually embed both translations and their contexts in the same latent space using something known as canonical correlations analysis. And so when we get a new context, for example, welche Fragen werden Sie heute fragen, we can automatically take that context and embed it in the same space and then do a k-nearest neighbor search and figure out which are the translations that are closest to this context. So that's something that I'm actually working on right now. In terms of other applications, or maybe applications, I'm speculating a bit here, but maybe applications that could help you. One thing that definitely I was thinking about is maybe monolingual phrase alignment. I know a bunch of you have worked on this kind of stuff. And so, there was a paper recently that was looking at semi-Markov states, for example, to try and break down the Markov assumptions and to try and take into account phrasal alignment. That's something that could actually be done somewhat similarly within a latent variable model. So this is actually an example from one of your papers, I believe. And so you might have, for example, you're looking at the alignment of closed up and closed down. In this monolingual alignment. What you could also do instead is look at the alignment between up and down and then attach to up a bunch of latent states that will then say, oh, in these particular contexts, this is a very high likely alignment here. So that's something that could also be done using latent states, and that's something that might be interesting to do. Another thing that's actually somewhat relevant is there's been some recent work on discourse parsing using essentially lower dimensional representations. And there what they do is they kind of dually learn or jointly learn both the representation as well as the actual the weights that help classify whether you should do a shift or a reduce in this discourse parser. But something very similar can be done in our case. There's been some work on latent variable shift reduce parsers, and I would be actually interested in kind of exploring some of these applications of these latent variable grammars in other areas, which I think may also be relevant to you. So the basic idea here is we start with this minimal grammar, and then we attach latent states to the non-terminals. We can do parameter estimation through a couple of different ways, and we get really good performance. So now I'm also just going to talk about the semi-supervised extension of a lot of this work. And so the basic idea is, in translation, what we want to do is, a lot of times parallel data is not as easy to get. It's scarce, it's harder to get in domains that aren't as easily available and the like. And so what we'd like to do is we'd like to take a small seed translation model that might have been extracted from a parallel corpus and enrich it with unlabeled data in a context-dependent manner. So the basic idea here is we're going to use a large amount of monolingual data to construct graphs, and we're going to construct graphs in two different languages, in the source language and the target language. And we're going to figure out, basically, based on the graph structure, we're going to propagate information through the graphs and be able to, we're also going to embed unlabeled phrases that we don't have translations for in this graph, and we're going to be able to figure out what their translations are based on how they are structured and how they're embedded in this graph. So this is the basic idea here. So we have our translation model, an a priori translation model. We have some unlabeled source, we have a bunch of source phrases. Some of them, we have a list of source phrases, say from an evaluation corpus. Some of them may be labeled, some of them may be unlabeled. The ones that are labeled and unlabeled, we embed them all in a graph together. We do a couple of extra things, basically, including this generation step, which I'll talk about briefly. But then the basic idea is then in the graph, we have these black nodes which are labeled, and we have their translations. Their labels are actually, you can think about it as being tables or multinomial distributions over words in the other language. And then we want to figure out basically what the translations are for some of these unknown words. And we're also going to take into account the structure of the label space as well. Yes, sir.
In the monolingual graphs that you're showing, are the nodes words or phrases? Either?
They are words and phrases. So in the experiments I run, I did unigrams and bigrams. Could potentially go higher though, but at some computational.
And the edges are co-occurrence?
The edges are based off of some co-occurrence. So the way I calculate it in my graphs is I use distribution similarity, scaled it to PMI, things like that, some standard techniques basically. But you can also construct these graphs using other ways, absolutely. All right, so as I mentioned, basically, we have this graph. And the first thing we'd like to do, actually, is so what we're going to actually do is we have this graph here, and the label space, as I mentioned, the cats, the dog, that label space can also be structured. So that label space also has some structure. We can also use monolingual data to embed that label space in a graph. But the problem with a lot of these structured output spaces, so especially when we're talking about phrases, is that the space is obviously very large, and it's actually not very likely. We're actually not going to get a very rich space using just the phrases that we've extracted from our phrase table. So just to make this more concrete, what we would like to do, for example, so in the case of felino, or un gato rather, if we have un gato and say el gato was already in the corpus and the like, what we would ideally like to do here is we would like to enrich the target side graph with candidates for un gato that are more likely than maybe what we have already seen. And we can actually enrich the target side of the graph using other external sources of information. So one nice example is morphological information. So for example, what you might see a lot in morphologically rich languages is you might see one particular morphological form, say attempted in the corpus, in your translation model, but you might have not seen other kinds of morphological forms of that word. So attempts, maybe English is not the best language, but attempts, attempt and the like. And so what, you might get a test sentence that might be more along those morphological forms than what you have in your model. And so you can actually use external linguistic information. You can use a morphological generator to kind of seed the target side of the graph with additional richer translations. You can use coarser models, so I can take my unlabeled phrase, I can pass it through my baseline system, and I can see what candidates it generates. And those candidates can also be thrown into the graph, and I can actually estimate the likelihood of those candidates being translations based on the distributional information and based on the graph structure. All right, so let me just, so this is the important slide that I wanted to talk about here. So how exactly do we do this inference over unlabeled nodes? So this is the example that we have. Yes, please. Oh, okay, thank you. So this is the example that we have, los gatos, el gato, un gato. And recall that the labels are these categorical distributions here. So what we can do is we can actually do regular label propagation and basically look at, for example, the potential candidates for an unlabeled source phrase and see, based on how similar these two edges are, based on how similar the el gato, un gato edges, propagate information from here to here proportional to the strength of that edge. Notice, though, that we're only taking into account the edge strength on the source side of the graph. So if I'm translating from Spanish to English here, I'm literally only looking at the Spanish graph here. But we can also do something known as structured label propagation, which, as I mentioned, the label space is also structured in a graph-like format. So what we would ideally like to do is not only take into account the similarities on the source side, in other words, how similar is el gato to un gato, because that should dictate or determine to what extent the cat is a translation for a cat based on that similarity. But also over here, how similar are these candidates to the other candidates here? So we have the cat from El Gato, we have a cat which is from Un Gato. How similar are those two candidates based on distributional similarity? And so what we do is we can propagate information proportional to both the source side as well as the target side to come up with better candidates and to come up with better translations. So we evaluated this on an Arabic English and Urdu English setup. And this is a bunch of numbers, but I just kind of wanted to emphasize a couple of things here. So if we look at structured label propagation versus label propagation, which I just spoke about now, we get quite a bit of gains, actually. So if you look at SLP 2 gram versus LP 2 gram, twice is better. We also, by adding morphological candidates to our target side graph, we can get even better performance. And the bullet point that I like here is that we then trained a very large language model, a 5 gram language model, 7.6 billion tokens. And the thing is, we threw that into the setup and we got even better improvements, which indicates to me that we're doing something orthogonal here to what the language model is providing.
The motivation was that it was semi-supervised, so you didn't have a lot of training data available.
Oh, but we have a lot of monolingual data available.
No, I know, but why use Arabic English?
So let's move on to the next situation. That was a medium scale data set. So we wanted to investigate it over there. I agree with your motivation. And that we then looked at this Urdu English data set. And this is actually a much more realistic scenario because we have a baseline setup, which is a fairly small setup, but then we have a bunch of noisy data. And the noisy data is sometimes parallel, but not all the times, not parallel all the time. And so one interesting experiment actually is if we assume that the noisy data was completely monolingual, we get roughly a gain of 25.3, we get a plus 4.2 gain. And instead, if we took that data and cleaned it up actually and spent a bunch of time cleaning it up and then we threw it into the baseline, we actually, we got a better gain. But the interesting thing is we spent a lot of effort actually cleaning up the noisy data and throwing it into the baseline. Whereas over here, we didn't spend any of that effort at all and we got 2/3 of the gains basically compared to this.
What's your baseline? Is it just a high-risk?
It's the NIST. It's, I think, the NIST 2009-2010 system, Urdu English. There was one, WMT, I forgot which one. One of those evaluations, basically. There was a standard Urdu evaluation for NIST or WMT, and that was the baseline. NIST, actually, yes. Some sample outputs. Actually, most of them are very good, but this is actually an interesting one that I'd like to point out because the reference is Abdul Mahmood. No, sorry, this is my mistake. I think I changed these, never mind. There was one example that I had where basically it relied too much on the distributional hypothesis. So I think it was saying Abdul Rahman, which is a more, and I think Abdullah is a more common name than Abdul Rahman. And so it proposed Abdul Rahman as the translation. So that was just kind of an interesting example. In terms of other applications, and then I'll wrap up after a few slides, just briefly talking about the segmentation stuff. But in terms of other applications, we have social media text normalization. So this is something I've been playing around with. But the basic idea is you might have something along the following lines, and you need to figure out, and as a pre-processing step into your systems, you need to normalize that. And so you can actually set it up in a very similar way based on initial seed training data. And I know a lot of these techniques, a lot of these graph-based semi-supervised learning techniques have been used by Partha Talukdar and others on Freebase, for example. So I believe for class instance acquisition or for enriching Freebase and for knowledge bases, a lot of people have used a lot of these graph propagation techniques. The classic example here, I guess, from their paper being if you have Bob Dylan, Johnny Cash, and Billy Joel being musicians, but you only, Bob Dylan, Johnny Cash, and Billy Joel being singers, and the musicians, you only have Johnny Cash and Billy Joel. How do you infer that strength of that red edge? And this is a classic graph propagation problem in some sense. All right, so in this particular section of the work, we had a graph-based approach to enrich a translation model using lots of unlabeled data. And as I mentioned, a lot of these ideas could be used to enhance free-based knowledge base or knowledge base and KBs of all sorts could be used towards paraphrase or question answering models. We got significant improvements on two fairly difficult language pairs, I would say, and there are various extensions that utilize, say, continuous representations instead. So this is actually a very quick part, so I'll actually just very briefly talk about this. The basic idea that we want to do is we want to just learn compositional functions, and for MT, compositional functions and non-compositionality is very important from a couple of different ways. You obviously don't want to translate hot dog like that. You don't want to basically, also as I mentioned, it's an extremely important source for phrasal segmentation. If you have a phrase that you know is non-compositional, ideally it should translate non-compositionally or translate as a unit. So we basically model these using a couple of different bilinear maps where you have your input vectors here, and we learn these particular parameters, look at multiplicative and additive models basically, or concatenative and tensor-based models. And the important thing, though, is where exactly do we get this supervision? Because I can get these word vectors a priori, say word to vec, or some distributional vectors and so forth. But how do I learn these parameters? I need some kind of a mapping. What's on the other side of that mapping? We can use the paraphrase database for this kind of stuff. We can estimate it with regularization and the like. And paraphrase database has this kind of information. You'll have like something like official that maps to staff member, youth that maps to young people. It's not exactly the same, but there's a heavy semantic equivalence. We get performance roughly as good as some of the previous state-of-the-art on some of the phrase similarity tasks. This is actually just an interesting heat map that I wanted to show. This is exactly what we learn from paraphrases. So in determiner nouns, you'll see that the determiner doesn't have much information on the semantics of the compositional phrase. In noun nouns, in compound nouns, you'll see that this is a lot more even. And then what we do is we use those vectors to compute, to basically come up with scores for phrases. So if I have a phrase like White House, I can score on a level from 0 to 1 how compositional it is. And we parameterize that in a very similar way to the skipgram model. The baseline is actually a context-independent model, basically, where if I have the vector representation for White House and have the vector representation for white and house, I simply take a weighted average of their dot products, basically with each other. So this dot product and this dot product. This is a context-independent way of figuring out how compositional a phrase is, and I can do it in a context-dependent way. The context-dependent way is naturally better. You can take into account the fact that heavy metal, for example, could be compositional in the sense that I'm talking about lead or iron or whatever, or it could be non-compositional in the sense that I'm talking about the music. And so a lot of whether a phrase is non-compositional is very context-dependent. We integrated this into machine translation and showed decent improvements. The bold results are statistically significant for p less 0.01. P-value, and the variances are basically in the parentheses. So we got a 0.4 blue point improvement, which is not as significant as we would have hoped, but it's decent enough. And so just to conclude very quickly, what I wanted to basically put across today is context obviously matters in translation, but instead of kind of looking at just the surface forms, so in other words, instead of just stuffing more words into a translation rule and making a translation rule larger, and that's what I would call a surface form or a word ID way of kind of looking at context, it's better to take a low dimensional view for tractability reasons. And whether that low dimensional view be something like I said, a latent variable model, which we learned through singular value decomposition, or whether that be a graph embedding, so whether we embed nodes in a graph and then we using the context and then propagate based on that. They provide various tractability improvements. The thing is about context is that it's largely unsupervised. We can extract a lot of interesting information using very little supervision, but the way we want to fit and utilize context in our models is obviously going to dictate how much supervision we need. And so I went through somewhat of a gamut of different levels of supervision and what we can do. And the basic idea that I'd like you to keep in mind here is that more context in MT doesn't necessarily result in larger units and larger models. And so with that, I'm done. Thank you.